Hello and welcome to Parallel Testing with Ractors, putting CPUs to work. My name is Vinny. I'm a senior developer at Shopify, where I'm a part of the Ruby types team. We work with Sorbet, Tapioca, Spoon, everything related to typing, and we are hiring, so if you're interested in joining us, please reach out. And if you want to know a little bit more about my work, you can find me at Vinicius Stock on both Twitter and GitHub. During RubyConf 2020, we got the first Ractor demonstration by Koichi right before Ruby 3 was released. And one of the things that I really wanted to explore was whether building a parallel test framework using Ractors would be any different or provide any benefits in respect to our current implementations. So today we're going to take a look at a few test execution strategies. We'll see an introduction to Ractors and how they communicate. We will build a test framework like Minitest, parallelize it using Ractors, and then we're going to take a look at a few highlights, features, and limitations of this framework we built. So how do we run tests? What does it mean to execute a test? Tests are just pieces of code, snippets of code that we need to organize and run. It's basically that. It doesn't matter if you're using Minitest and the blocks are test methods, or if you're using RSpec and they're regular Ruby blocks. They're just a piece of code that we have to organize and execute. It then becomes a matter of how can we do that fast? How can we execute those pieces of code faster? Which is when we start getting into parallelizing tests, and we're going to take a look at a few execution strategies for doing that. So the first strategy is by dividing the tests into different groups. We start by figuring out the test we want to run. We randomize the tests into groups. And then each group gets assigned to a different CPU, to a different parallel worker that's going to run that simultaneously. It's a simple strategy, but it does have one major flaw. It does not guarantee even distribution in terms of the amount of time it takes to run the tests. So for example, if we end up in a situation like this, CPU 1 got unlucky, it got more tests than CPU 2, and it got 2 integration tests, which are slower than unit tests, then it's very likely that CPU 2 is going to burn through its group significantly faster than CPU 1, and it's just going to be idle waiting for CPU 1 to finish, when it could actually continue doing more work for us. So execution strategy number 2 tries to address this by using a queue mechanism. We begin just the same by figuring out the tests we want to run, and then we randomize our tests into a queue. So each individual test example becomes an item in our queue. And then our workers, our CPUs, can pull items from this queue as soon as they're ready to do more work. So for Minitest, it would look something like this. Each item in the queue is an individual test method, an individual test, and the workers can pop items from the queue as soon as they're ready to do more work, avoiding being idle until the very end of the suite. But originally, Ruby did not have support for taking advantage of all of these different CPUs we have available. So how can we parallelize tests now? How do we currently do it? For example, Rails ships with a Minitest plugin that allows us to run our tests in parallel. How does it actually work? Well, it uses execution strategy number 2 by using a queue object to organize our tests into our individual tests into a list. And for the parallel workers, it forks different Ruby processes, different child processes that will run those tests in parallel. It then becomes a matter of how do we organize this, how do we communicate between the workers and the main process to be able to delegate the work. And Rails, in this case, uses a gem called DRB, which stands for Distributed Ruby, in order to handle inter-process communication. This gem provides us a means of sharing a Ruby object between different processes. So in this case, the main process shares the queue object with all of the workers, and the workers can just regularly pop items from that queue and do more work as soon as they're ready to do so. But now we have Ractors, so can they perform any different than processes? Let's begin with a few examples of using Ractors. So you can create a new Ractor just by using new, like any other Ruby object. And here we're creating a worker that is going to do two things. It's going to receive an item. So Ractor receives a message that's being sent to this worker. And after we receive that, we're going to do some processing on it. So as we reach this point in the code, we're going to be stuck waiting. The worker is going to be stuck waiting for a message. We can send it some important information to begin processing. And then we can use take to wait until that worker is done and take the return value of process. A more involved example that we're going to use in our framework is a worker pool. So in this case, we begin with a queue of numbers from 0 to 99. We create an array to store the results of our calculations. And then we create our worker pool, which is an array of reactors, in this case 10 reactors, and each one of them is going to be stuck in an infinite loop, and we're going to do two things inside of it. We're going to receive a number that's being sent to this worker, and we're going to yield back that number times 5. So in this case, reactor yield is typically used when we need to return values from reactors at multiple times during the execution. In this case, for every iteration of our loop, we're going to receive a number, and we're going to have to return that number back to the main reactor to store our calculations. We know the workers are going to be stuck waiting to receive a message, so we can kick all of them off by looping through each one of them and sending them an item from the queue. And then until our queue is empty, we can use Ractor select to find the first idle worker and the result that that worker has yielded back to us. We save the result in our array, and we can send the idle worker another number from our queue so that it can continue doing more calculations for us. Notice that this loop ends when the queue is empty, but we can still have reactors running in the background and yielding values back to us. So we still need to go through each one of the workers, make sure they are done with their calculations and take their return values back. Let's give reactors a little bit of a break. We need to take a look at how test frameworks work in order to be able to build one and parallelize it. So I like to divide them into 3 areas of concern. We have execution. So how do we organize all of the pieces of code we have to run, all of the tests? How do we create our queue and dispatch the work to all of the different parallel workers? Utilities and syntax, which is how do we actually test our application code? Do we use assertions or expectations? Are there mocks and stubs available? And reporting is how do we display information to the user? If we start taking a look at the code here on the left based on Minitest, we can start extracting a few concepts that we're going to be using to build our framework. So the first thing I want to call attention to is that the tests files are just regular classes. Tests are just regular classes in Minitest. So we can just require the files under the test folder to be able to load them. But they are of special interest to us. We need to be able to keep track of them so that we can reference them later. And we know that each one of these classes can define multiple test methods. So we need to be able to loop through each one of the test classes, but also run each one of the tests defined in them. If we zoom in to inside a specific test, we start getting into how do we verify that our application code works. So we start looking into assertions and how we define the syntax to be able to write our tests. It needs to assist with execution flow as well. So if an assertion fails, there's no point in continuing to run that test. We can mark it as a failure and move on to the next test we have to run. It needs to save information about failures and any other statistic we like in order to be able to display that to the user at the end. And it can provide any helpers or quality of life utilities that we like. So mocks, stubs, maybe date helpers, anything we like. Finally, reporting is responsible for 2 things. We need to be able to display progress to the user. So here are the dots on the screen. And we need to be able to display aggregate results about all of the tests we run at the end. So here's the statistics about assertions, failures, and that kind of thing. Let's actually get down to implementing it. And we'll begin by thinking about how we can keep a reference to each one of the test classes. We know we're going to be requiring the files under test, but how can we keep track of the classes? Well, Ruby has exactly what we need. If we create a class method named inherited in a base class test, Ruby is going to invoke that for us every time something inherits from that class. So we can define that all the tests need to inherit from our base class, and when Ruby invokes this callback for us, we can just save the class that has inherited our base class in an array, which is already enough to keep track of all of the test classes we required. But how do we model our test queue? Because we're saving the test classes, but we know that each one of them can define multiple tests, can have different test methods. So we need each one of these test methods to become an individual item in our queue. We need something that looks kind of like this, an array of tuples, where each tuple is composed of the test that we want to run and the class that that method belongs to. So we have the list of classes. We can try to remap it and build the queue in the format that we are expecting. So we remap each one of the classes, and for each class we're going to list all of the available methods, the instance methods, and here false just ignores inherited methods. And then we're going to filter them out based on whether they begin with test or not, because we're not interested in listing setup, teardown, or any other helper method that the user might have defined. We're just interested in the test methods. After we have the list of test methods, then we can actually return each one of the tuples with the class and the method name to match exactly what we were expecting for our queue. So now we have the our entire collection of tests are organized in this queue. We required the files, we were able to list all of the test classes, and we have each one of the tests individually inserted in our queue. But we need to be able to take each one of those entries and actually execute them. So we need to define how to execute them. We begin by creating a new instance of the test class we are receiving from the queue. This is very important for isolation. So if each one of the tests runs in a separate instance, then we don't have to worry about changing instance variables or any data inside the tests. They're going to be isolated. It's not going to have there's not going to be any conflicts between each one of the tests. And with the instance in hand, we can invoke methods on it to define each one of the steps for running a single test. So we can do setup in the beginning. We can dynamically dispatch the method name we received from the queue, and then we can invoke teardown to finalize the test, which is already enough for very basic execution. But of course, it's not very useful at this point because we can't actually assert anything. So let's build assertions. The most basic assertion is just asserting whether something is truthy or falsy. And of course, there are only two possibilities. Either it passes and it is truthy. In that case, we want to just continue running our tests. We don't want to do anything other than maybe recording statistics. But if it fails, then we do have a few things we need to do. We need to save information about that failure for later. In this case, we typically use a reporter class in a singleton pattern, so in a class variable, to be able to aggregate information about all of our tests that are running and display everything, the aggregated summary at the end. And after saving information, we need to be able to skip to the next item in the queue. Again, there's no point in continuing to running the test if we already know it has failed. So this is what it would look like in code. We begin the assert method by incrementing the total number of assertions, so just some statistics. The happy path here, if something is truthy, we return early, so nothing happens. But if we fail, then we continue on this method, and we can register that failure with some information. In this case, we're using a failure message and the current instance of the test, so we have as much information available as we need to display a nice message at the end for our users. Finally, we need to be able to skip to the next item in the queue, so we can raise a custom error class that we control in order to rescue it at a higher level and stop executing the current method and move on to the next item in the queue. And for each one of the failures, we can take advantage of that to print some progress and print an F to the screen. A few more statistics we can add if we go back to our execution steps. After we have the instance, we can begin by incrementing the total number of tests. We know that for each one of these items from the queue, we're running an individual test, a single unit, so we can increment the total number that we ran as we enter execution. The body of the test remains the same. We're still going to do setup, invoke the test method, and then teardown. And when we reach the end, we can increment the number of successful tests. The reason we can do that is because if any assertions fail during the body of our tests, we know we're going to raise a specific error class that we created, and we can rescue that at a higher level than this basic execution flow, which guarantees then that if we reach the end, it's a successful test run and we can increment the number of successful tests. Finally, when we increment it, we can print a dot to the screen and display some more progress. We have the basic blocks to be able to build our test framework, but we need to put the pieces together. So we'll begin by requiring each one of the files under test. This is already enough to populate our list of classes. And then we can loop through each one of our tuples, our test queue, and for each one of them, we'll take the class and the method name, and we're going to run the execution flow that we defined. As we go through the queue, we know that we're going to be populating our reporter with information about our tests in our singleton reporter class, So at the end, we can just print a summary because the singleton instance is going to have the entire information about our test run. And this is already enough for very simple sequential execution, but we're interested in parallelizing it using Ractors. So let's go back to our execution script here. We're going to begin just the same by requiring each one of the test files, and then we're going to assign our queue of tuples to a variable. Here we're shuffling just to randomize the order. And notice that we're going to use the same strategy as our worker pool example we saw before. So we're going to create a worker pool of Ractors, here using the total number of available processors. And each one of the Ractors is going to be stuck in a loop receiving tuples from the queue and then running our execution flow for each one of those tuples. So we're going to run each one of the tests we receive from our queue. We know they're going to be stuck waiting to receive a message, so we can send each one of the workers a test from our queue. And then until our queue is completely empty, we can find an idle worker and send it another item from the queue. So this should run the tests in parallel and populate our reporter for the end. But if we try to run this, we're going to find out that we're going to get an error. We're going to get an error related to using class variables inside non-main Ractors. So basically, Ruby currently does not allow you to use any class variables inside child Ractors. And this error is coming from our singleton reporter instance every time we try to access it to save information. So we need to be able to find a different way of aggregating information that doesn't involve class variables. One possible way of achieving this is by creating multiple reporter instances and aggregating information in an aggregator. So here in our main Ractor, we create a new reporter that's going to be responsible for aggregating information. And every time we execute our tests, we're going to have to yield back information about that test run so that we can take that information and save it in our aggregator. So in this case, every time we yield, we're going to get a temporary reporter back that has information about that particular run, and so we can concatenate it into our aggregator, save that information, and make sure we're aggregating without using class variables. At the end, we should remember to take all of the values that are still being yielded by the Ractor, so no information is missing. And we can now run tests in parallel. This is all we need in order to be able to run using Ractors. The biggest challenge is overcoming the singleton pattern in the reporter. And our framework is actually available on GitHub. It's called Loop, and you can check it out at Vinicius.com/loop. I want to do a bit of a demonstration of how it works. I want to show what loop can do out of the box. So I have a test suite ready, and loop can run our tests in both process mode and Ractor mode. And I just wanted to demonstrate the two modes in action. So first we'll start with process mode, and notice how it takes a little bit until it actually starts running our tests. This is the initial cost of forking the different Ruby processes compared to using Ractors. So with Ractors, we don't actually have that cost because there's only one Ruby process for spawning different Ractors. Additionally, I just wanted to display Loop's interactive reporter. So if we run it in the interactive mode, we'll get paginated results with all of the different failures in our test suite. We can cycle through each one of them and look at the highlighted file here using bat, and displaying also exactly what has failed in our test. We can click O to open this in our favorite text editor, and here we made a horrible mistake, so we must fix it. It allows us to rerun each one of the individual examples that we are working with, and then if we're happy with the result, we can mark it as fixed until we fix the entire suite and we're ready to move on. Thanks to Loop having both process and Ractor mode, we are able to measure the performance of the two modes and compare the two as we increase the number of tests. So here what I want to call attention to is that using processes has an initial cost that is a little bit higher than using Ractors. This cost comes from forking all of the different Ruby processes to create our worker pool. But as we increase the number of tests, the difference between Ractors and processes becomes smaller and smaller because we spend the majority of our time inside our application's code and not actually inside the test framework. So perhaps for long-running processes, the performance differences is not very significant. A few highlights of our framework, limitations and features. It cannot make broad usage of class variables as we've seen because the child Ractors don't have access to them. So we can only use it inside the main Ractor. It cannot make broad usage of dynamic methods or metaprogramming in general. So if we use the find method, for example, to create a method inside a Ractor, that method only exists in that Ractor and is not accessible by any of the other Ractors. So we need to be careful about that as well. And it can only test Ractor compatible code if we're using Ractor mode, of course. The reason for that is because the workers are all child Ractors, and our application code is going to be running inside one of those workers. So all of the limitations that child Ractors are subject to are going to be applied to our application code as well. So we're not going to be able to use broad class variable usage or too much meta programming, or else we're going to end up getting a few errors. The application code also needs to be Ractor compatible in order to run in Ractor mode. It can run our tests in parallel, which was our primary objective, and it can test code that spawns more Ractors. So we spawn a pool of workers, but what if the application that we're testing also creates more Ractors? That is completely fine. Thanks to the actern pattern, we can create as many Ractors we want, and as soon as there's a CPU available to pick it up, it's going to do the work for us. So that it works without any modification. And it doesn't pay the initial cost of forking processes. So perhaps for shorter-lived processes where the startup time is the biggest cost, then maybe this is a good solution. It can provide good performance benefits. As we were putting Loop to stress and really testing it out, my colleague Peter Zhu and I were able to find a few bugs in corner cases as we used the framework. So the first one we found was a segmentation fault whenever we were trying to yield values back from Ractors, exactly as the garbage collector was sweeping for freeing memory. Another one we found is that if we create classes inside Ractors, anonymous classes using class new, when they're ready to be freed, we also found a few segmentation faults as the GC is sweeping those classes. And finally, we found a deadlock when referencing an autoloaded constant for the first time inside the reactor. So if the first reference we ever do to an autoloaded constant comes from inside the child reactor, it would cause a deadlock. And I'm happy to announce that we managed to fix the first one, but we haven't been able to get to the other ones just yet. So reactors still have a few limitations, and we've seen that our framework has those limitations as well. But the reality is that they're still experimental, and they will continue to evolve. Developer tools are a great opportunity to test reactors and technologies like that, because we don't have a high-risk environment such as our production servers. We can really take advantage of that to test it out, find problems, provide feedback, and help shape the future of Ruby parallelism. Thank you so much for listening to me, and I hope you have a great rest of the conference.